Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 52. My name is Allergies Joseph Darnell, and I'm joined by the doctor, who cannot help me, Robert Carter. Hello, Rob. How you doing?
Joe, it sounds like you have cotton in your throat.
I have
your
a growth.
Deep resonant voice is just a little bit like this.
Sore, hoarse. Yeah, so I'm not used to Georgia allergies giving us a sore throat. So this is new. I'm trying this year. Other people are too. It's the latest rage. It's trending in Georgia. Hashtag Georgia, hashtag trend. And I'm done with it, to be honest. I think I'm going to return it. I do not recommend.
Okay. Well, I tell you that this is the weirdest spring that I ever remember. I've been through a lot of springs here in Georgia, but it was 32 degrees this morning. It's late April. That's not supposed to happen in Georgia. That's February weather.
Yeah, my birthday is April 14th, and I don't think it's ever dropped below freezing in this metro Atlanta area in my lifetime after my birthday.
So I don't know what that's doing to the pollen cycle, or to which trees are blooming or not blooming, or how much they're blooming, but some weird things are happening. Something is amiss.
Now, you want to go down into the honeybee topic just for a split second?
Sure, what you got?
You were telling us about your temperature gauge.
Yes.
How did that turn out to be useful in this situation?
Well, I was able to monitor inside my beehive from the comfort of my home as the temperature plunged to 32 degrees or 0 C on my gauges. And I was able to look inside the beehive and see that they were maintaining their temperature 20 degrees above the outside temperature.
Nice.
I was happy. I was really happy. And that my temperature gauge is on the outside wall of the beehive. And so I'm just getting like the spillover. They're probably massed in a ball in the middle of the hive, all huddled together. And yet, even away from that ball of bees on the edge of the hive, it was still considerably warmer than the outside air. And they've only been in there 2 weeks now. They haven't filled up that box with comb yet. After they do that, the temperature inside will be a lot more stable. And there'll be more bees also when that new crop of bees starts to hatch. There'll be more bees for more heat. They'll have a better control of everything. But so far, so good. I'm really, really happy with it.
Awesome.
And they're maintaining their internal humidity about 75%. And that's irrelevant as far as what happens outside. They're just maintaining it nice and steady.
So how did they maintain the humidity? Is it just because their body is producing that much and consumes that? I mean, honestly, you say they're controlling the humidity. How did they do that?
Well, one thing they'll do, I haven't seen much of it, I've seen a little bit of it, is they will station bees at the entrance, some of them pointing inwards and some of them pointing outwards, and they'll just beat their wings with their butts up in the air. And they're just circulating air into the hive and out of the hive. And so they're just, it's not passive, it's active air exchange.
Huh, okay.
Yeah.
Interesting. I haven't looked at my bees in a couple of days, but I'm sure they survived. If yours survived, mine survived.
There'll be a lot more in the middle of summertime. There'll be a lot more of that. You'll see it.
Well, I don't have a whole lot else to talk about. I'm actually tempted to put myself on mute so that we don't cough in the audience's ears. I think that would be the best thing for all of us.
All right, but you got to ask me questions though, because I designed this as in, if Joe's going to ask me this question, I'm going to have to answer it.
Yeah.
And I'm in dread because there's like 100 questions you could ask me that I can't answer. But
I'll do my best. Jinx. What I typically will do is I'll put a pin in the question until you pause for a breath, and then I'll unmute and I'll ask.
All right. Well, I don't have a lot of chit-chat this week either because my main chit-chat item became the topic. As I was thinking about it, I was like, wait, we've got to do that for the topic. And so I just spent hours researching and writing and thinking and doing math and graphs. And because do you remember when we did gravity?
Yeah.
Oh no, tides. Remember when we did tides?
Them too.
And I said, this is the way I wanted tides explained to me.
Yeah.
Well, this is a similar thing. This is going to be, here's how I would want black holes explained to me.
That's a great rule of thumb.
And we're going to approach it from a very different direction than most people might think.
Okay, so I'm about to cough, so I'm going to mute.
All right.
Goodbye.
Well, an amazing thing happened just this week. Some scientists announced that they discovered a black hole, which was very small and very close to Earth. I mean, small, it's only 3 solar masses. It's only 3 times as large as the sun, or as massive as the sun. And it was orbiting a red giant star in the constellation Monoceros. And of course, mono Ceres is unicorn. So they gave it the nickname the unicorn. So we have this tiny little black hole. And the question is, how did they detect it? You can't see black holes, especially small ones. Well, because it's orbiting a star, the star wobbles and the star gets stretched. And they knew that there was something that had a lot of mass orbiting the star. But if you can't see it and it has mass, well, that's kind of the definition of a black hole. And so they calculated this was actually a black hole orbiting the star. They know how far away it is and how big it is. It's just really cool. Nice observational science. Kudos to the scientists who figured this out. And that brings in a lot of other questions, doesn't it? Like, what is a black hole? Do they really exist?
Well, I wonder on that note, how did people even suspect they were a thing in the first place? How did we stumble across evidence to suspect that there were black holes?
Well, the first black hole concept was actually from the 1700s. Back when they thought that light was corpuscles or particles. Well, particles have to have mass. And if Newton was correct about his gravity theory, then light would be affected by gravity. And someone, like 1790 something, he said, wait a second. If you had something with enough mass, light could never escape it. Now, not the same concept as our event horizon black hole that we have today, because basically, if you're standing on Earth and you throw a ball up in the air, it'll slow down and then fall back to Earth. Well, this guy's concept was, well, if you have a massive object and light is leaving that object, it'll slow down, turn around, and fall back again. So it can get away from the object, it just can't escape it forever. And so he wouldn't have called it a black hole, but it's a very similar idea. The idea that light is attracted to gravitational sources, and if you get a big enough gravitational source, you can't get away. Einstein published his general theory of relativity in 1915. This is all these ideas that, you have length contraction and time contraction and all these weird things happening, but speed of light never changes. No, it's always the same. And when you throw gravity into that mix, you get Einstein's general theory of relativity. But the formulas are opaque. The formulas were laborious. I mean, I've looked at these formulas and I'm like, oh, groan. I don't ever want to have to do math like that. But this guy named Schwartz, he reworks these formulas and he comes out with something we now call the Schwartz radius. That is, what is the diameter of a black hole? Given the amount of mass you have, what's the diameter of the black hole? That's called the Schwartz radius. And really interesting, we're going to talk about three different formulas here. And they're all very similar to one another. We have the gravitational formula, the escape velocity formula, and the Schwartz radius. The physics isn't really that hard if you come about it in the right direction. So you remember Newton and his gravitational formula. Do you remember what the gravitational formula was?
No, that was episode 1.
Well, it's the force, the gravitational force, equals some constant times mass 1 times mass 2. So in other words, the greater the masses, the greater the force. But then you divide it by the distance between the masses squared. So gravity doesn't drop off with distance, it drops off exponentially with distance. If you double the distance between two objects, the gravitational force goes down by 4, because 2 squared is 4. So it goes down exponentially. It took us forever to figure out what the constant G was. We did talk about that. It was in 1800s. Cavendish, I think, was the guy who figured it out with his lead balls suspended by a wire, a torsion spring. But it's a very convoluted number. It's 6.67 times 10 to negative 11 meters cubed, kilograms, or per kilogram per second squared, or something like that. And so when you throw that G times mass, which is kilograms, times mass, which is kilograms, divide by the radius squared, which is in meters, it comes out to newtons, or kilogram meters per second squared. So a 1 kilogram object produces 9.8 newtons of force in Earth's gravity. Okay, way too complicated. Let's make this more simple. The audience is turning over. They're probably reaching for the off switch right now. Let's make this really easy.
Well, Rob, I have a question.
Yes.
Along the way, when you're ready, can you explain what determines the size of the black hole? And
yes,
we were talking about science fiction the other day. It seems like in the movies, they arbitrarily may or may not use black holes to get bigger and smaller. So as it's convenient to the plot.
What do you mean to get bigger and for themselves to get bigger and smaller?
Mm-hmm. Yeah, so I wonder, do black holes change size and why on earth would they do that?
Oh, well, the answer is yes, they do. And the size of a black hole is only dependent upon the mass of the stuff that's inside the black hole. That's it. We'll get there in a second. I want to talk about, to understand why light can't escape a black hole, let's talk about the escape velocity formula. We've seen a lot of rockets blasting off from Earth lately. SpaceX, they're launching like crazy. But to get out of Earth's atmosphere, to get away from the Earth and to fly off into the solar system, you've got to be moving at 11 kilometers per second. That's how fast from ground level. So if you could like all of a sudden, boom, and move at 11 kilometers per second, you'd fall off the Earth and go away forever. Anything less than that, you might go up really high and eventually you're going to fall down again and crash back to Earth. In physics class, every high school student in physics, Johnny hits the ball upwards at a velocity of 6 meters per second. How long will it take the ball to fall back down to Earth? And actually, the formula for that is really simple. It's just this versus minus this. And all you have to understand is that on the Earth, the acceleration is 9.8 meters per second squared. So you get faster and faster and faster and faster the longer you're falling. And if you send something up, it's going to slow down, slow down, slow down, slow down, slow down. But if you can send it up fast enough, Earth cannot possibly slow it down all the way. And that magic number is just over 11 kilometers per second, which is really fast. But I went ahead and calculated a whole bunch of escape velocities for different things based on their mass. So if you want to get away from the sun, you got to move pretty fast. You got to move at, let's see, if the Earth is there, it's probably 800. I'm guessing, I'm going to look it up on my chart because I still have my Excel thing open. If you want to get away from the sun, got to go to the right column on my thing here. Yeah, you got to move at 617 kilometers per second. To get away from Earth, you only have to go at 11. So if you want to fly from Earth to like Pluto, you need a big old rocket. Most of the energy is not getting away from Earth. Most of the energy is getting away from the sun. The sun is a huge gravitational object. So if you launched at exactly 11.17 meters per second away from Earth, you could orbit the sun at that distance, but you couldn't get any further away from the sun because all you've done is escape Earth. You still have to escape the sun. Gravity is kind of cool that way. But if you took the mass of the galaxy and you were as far away from the edge of the galaxy as the average diameter of the galaxy, it's about the same velocity to get outside the galaxy as it is to get away from the sun. They're almost the same number. And the reason for that is we're really close to the sun. We're only a couple million miles away from the sun. We're still well within its gravity well. But if you take all the stars in a galaxy, as long as you're not next to any particular star, if you're out in the middle of nowhere in between stars, you need about as much velocity to get out of the galaxy to get to some other galaxy as you do just to get out of our solar system. So far, so good?
Yep.
Do we understand escape velocity?
Yes.
Okay.
On escape velocity,
yeah.
Does that explain why, things that are flying through the air,
yes,
whether they're birds and insects and planes, they are orbiting the Earth at the same time that they're also, going this way and turning around and going back the other way.
Yes.
So a plane traveling straight north over the Earth is also rotating with it.
Yes.
Does this pertain to the escape velocity?
No, because we're
Not
talking
really?
about things moving so slow compared to 11,000 kilometers per second.
Okay.
It's not comparable. If you're orbiting, you have to move sideways at a certain velocity. If you exceed that speed, you're going to drift away from the Earth. That's an interesting question. I've never actually thought about that. I'm now going to have to do a graph of orbital velocity versus distance from the Earth, etc. But yeah, if you're moving that fast, Earth's gravity can't hold you in no matter what. And the smaller the gravitational body is, the less fast you have to go to get away from it. So to get away from the moon, I mean, you've only got to be moving 2 kilometers per second. That's still really fast. I mean, 2 kilometers, that's 1.2 miles per second. That's fast, but it's a lot less than the Earth and a whole lot less than the sun. Or even something like Jupiter. Like if you want to get in a rocket and go down to Jupiter and just touch the gas of Jupiter and then get away again, you have to move 60 kilometers per second to get away from Jupiter. That's 5 times or more faster than you have to move to get away from Earth. So you would need a rocket that doesn't exist. We can't actually touch the surface of Jupiter because we could never get away again. But I did think that what if we sent a big scoop, shoot it at I can't even talk. Shoot it at Jupiter and just clip the edge of it. And so it's moving really fast and boom, can we actually capture a part of Jupiter's atmosphere? And I think the answer is no, because as soon as you touch the atmosphere, the frictional drag is going to slow you down and you'll never get out again. But I'm not sure. That's kind of fun. Just things to throw around.
Yeah, interesting.
Okay, Another concept. Forget all the different bodies in the solar system that have different masses and whatever escape velocity you need. Let's just talk about the sun only. And the escape velocity you need to escape the solar system if you're at the distance of Mercury or the distance of Venus or the distance of Earth or the distance of Mars. Well, if you're only as far away as Mercury, you need a velocity of about 70 kilometers per second. If you're at the distance of Venus, it's about 50. And I think no, that's not true, because the sun is 617, and as you get over to Mercury, it's a lot less. So yeah, okay, I think that's about right. 70, Venus about 50, Earth is about 40 something, and it goes down, 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 down. So the further away you are when you start, the less velocity you need to escape the gravity of whatever you're trying to get away from. Does that make sense?
Yeah.
Okay, now we're going to talk about something weird. This is going to be different. All that groundwork laid down, think about the Earth. Great, 11,000 meters per second, or 11 kilometers per second, to get away from the Earth. Hey, audience, I'm throwing around a lot of numbers, and very often I get off by a factor of 10 when I have too many numbers in my head. So if I say 11,000 or 11 or something, and that's a factor of 1,000. But if I get off by a factor of 10, it's because I'm trying to do math in my head, and powers of 10, they kind of escape you sometimes. Just roll with it. All right. Just think of Earth. We're standing on the surface of the Earth. The radius of the Earth is 6.3 something million meters. 6,300 kilometers. 6.3 million meters. That's the radius of the Earth. And if you want to get off the Earth, you got to move upwards at 11,000 meters per second. Okay, let's reduce the radius of the Earth by 90%. Let's squish it down to only 637,000 kilometers. Now it's 1/10 the radius. Same mass. We just took all that iron and nickel in the core and squished it down to some improbable, unobtainium. You can't actually do this, but just imagine you take all that mass and you squish it down. Now the Earth is only 1/10 the radius. If you are standing in the same place and you didn't move, but the Earth shrunk underneath you, now you're hovering over this tiny little Earth. Your escape velocity is still 11,000 meters per second. If you're standing on the surface of that tiny Earth, your escape velocity would be 35,000 meters per second. So drop the radius 90%, your escape velocity more than triples. But if you stay in other words, if the center of the Earth is 6.3 million meters away from you, and you shrink the size of the Earth, but you're not touching the Earth, you're still 6.3 million meters away from the center, the mass is the same, your escape velocity is the same. But if you now get in a rocket and slowly go down, and now you're standing on the surface of the tiny Earth, well, you're very deep into the gravity well. And you need a lot more energy to get away. Because in the formula, the escape velocity formula, it's 2 times g times m divided by r. So the smaller the radius is, the greater your escape velocity, even though your mass hasn't changed. If we take that Earth and now make it 90% smaller, now it's only 63 kilometers, or it's about maybe 40 miles in radius. You have to move at 111,000 kilometers per second to get off of a sphere that small and that dense. Go down another 90%. Now it's only 6.3 kilometers, maybe 4 miles in radius. You got to move at 352,000 meters per second. What's the speed of light? Well, it's 30 million meters per second. We're getting close. If you reduce the size of that sphere even more, it makes the Earth unbelievably dense. Same mass, but small. Let's say we get down to 637 meters. You got to be moving at over 1 million meters per second to escape that. There's no rocket in the world that will ever be able to do that. If you get down to 63 meters, that's less than 100 yards now, 63 meters, you got to be moving at 3.5 million meters per second. You get down to 6 meters, you got to be moving at 11 million meters per second. Here's the deal. You get down to 10, 100,000, 100,000 million. It looks like we're like 1/10 millionth the size. The Earth is now 0.63 meters. I think I got a factor of 10 off here. Anyway, you now have to be moving at 35 million meters per second, which is faster than the speed of light. Now the Earth is a black hole. The black hole size of the Earth, if you could take the Earth and squish it into something that's less than a centimeter, it will become a black hole. Using a very simple idea that the escape velocity is proportional to the mass divided by the radius. This is true for any object in the universe, except for some tiny little objects, but any object of any significant mass, if you squish it down to a small enough size, if you're right next to that object, you can never get away. It will capture you forever. We okay?
Yep. I'm just plugging away here on my thoughts and working on some special custom show art for today's episode.
All right. Well, that's my groundwork. That is the beginning of the idea of black holes. It's just escape velocity. And escape velocity just depends on how massive is your object and how close are you to it. Well, light is velocity, or light travels at a constant velocity. And therefore, if you have something that's massive enough, and if you're close enough, your escape velocity becomes greater than light speed, and you're trapped. That is a black hole. This is what everyone realized after Einstein published his general theory of relativity. And this is what Schwartz formulated. We have this thing called the Schwartz radius. I love this. I used to have a shirt that had the formula on it, and then a picture of a black hole, but it was the mathematical expression of a black hole, just like a funnel. And the formula is, so the gravity formula is 2gmm over r squared. The escape velocity formula is, gravity is gmm over r squared. Escape velocity was 2gm over r, and the Schwarzschild radius is 2gm over c squared. Those formulas are very similar to one another. But if you take any object, you can calculate at what size that mass. So if you took the Earth, you could calculate the size the Earth would have to be before it becomes a black hole, and we just did that. You could take the sun. How small can you make the sun before it becomes a black hole? How small can you make the moon? How small can you make a watermelon before it becomes a black hole?
Wait, what?
Any object.
So it's not important that a black hole is gargantuan. It could technically be the size of a baseball?
Thank you for the question. Yes. Yes, yes, yes. It's just mass in a volume. You can have a tiny little black hole. Theoretically, they can exist. We'll get to how fast they evaporate and things like that in a little bit. But yes, anything theoretically from first principles can be a black hole if you squish it small enough, up to a limit, which we'll talk about. There's a couple of issues with black holes, though. If you want to form them spontaneously, they're not going to form all by themselves if you don't have at least 3 sun masses or 3 solar masses. And the reason for that is electrons repel each other. You need more than 3 solar masses to be able to crush atoms together. And if you don't have that, the thing's not going to collapse into a black hole. You can't get it dense enough to become a black hole if it's less than 3 solar masses. There's another cool way to make a black hole, though, which I hadn't considered before just recently. Let's say Jupiter falls into the sun, and Neptune and Uranus and the Earth and everything falls into the sun. Let's say the sun runs into Alpha Centauri and they merge, and then they run into Proxima Centauri and they merge, and we're getting more and more mass in one area. Well, eventually, if you keep on adding mass, you can make a black hole. Now, they've done calculations with just water. How much water would it take to make a black hole? And the answer is, if you had about 136 million solar masses of water, just floating in space in a sphere, it would morph into a black hole because the radius of that sphere is smaller than its Schwarzschild radius. The Schwarzschild number being 2gm mass over c squared. And all of a sudden, your giant ball of water disappears because it got a little bit too large and the Schwarzschild radius became larger than the radius of the object itself. So yeah, you could take a watermelon and squish it down to a very, very, very tiny point. It would become a black hole, or you could have 100 trillion watermelons floating in space and they become a black hole. Either way works. You don't need a lot of mass, but if you have a lot of mass in one spot, it will automatically happen. You all right so far?
Yeah, I'm actually doing pretty good at the moment.
Okay.
So a question about black holes.
Yeah.
Can you cough inside one?
Mm-hmm.
Okay.
You can live absolutely normal life inside a black hole and never notice.
See, that's another one of those things about being informed by science fiction.
Yes.
Some would imply that it's going to send you to another dimension, or it's going to crush you, or you'll suffocate.
Suck you in. We're falling a black hole. It's sucking us in.
Yeah. Now you're Alice falling into a bottomless pit.
Just ridiculous. But in one sense, some of the things that are portrayed make sense, and other things they just don't. Black holes don't suck any more than the sun does. If you had a black hole of 3 solar masses, it has the gravity of 3 suns. There's tons of stars in the universe that are bigger than our sun. Lots and lots and lots of them. It behaves according to the laws of gravity. It's not a vacuum cleaner. Anything falls towards anything else in a gravity world. They're not any more powerful than anything else based on the amount of mass they have. Literally, it's just based on the amount of mass that's there. That dictates how strong the gravitational attraction is. So they don't suck things in anymore. It's not like, I got too close. Not the way it works. The other thing, you can't ever get to the black hole. Well, that is, if you're on the outside watching someone falling toward a black hole, you'll never see the person enter the black hole. They'll just slow down and slow down and slow down. And yet the person falling into the black hole, he doesn't notice anything at all. Now, you might seem to be going really fast for him if he's looking at you, but time for him progresses normally. Just like time for you progresses normally, but if you're looking at each other, weird things are happening. But if you're falling into the black hole, you don't notice anything weird. In a couple of cases for black holes, because there are different sizes of black holes, and the size of the black hole makes all the difference. You could fall into a big one and never notice it. You can't fall into a little one without being ripped into pieces.
See, I did not expect that answer.
Remember our discussion on tides. The tidal force is different. Like if you put a big ball of water in our solar system, you get rid of all the planets, you got the sun, put a big ball of water in the solar system that's not orbiting the sun, and let go, it starts falling toward the sun. But the side closer to the sun is accelerating faster. It's falling faster than the side away from the sun. It's further away from the sun, there's less gravitational attraction. So your blob is going to start stretching because of what's called the tidal force. The tidal force is the difference in gravitational acceleration from one side of the object to the other. The blob will stretch. There's something else interesting. It'll get narrower. And not only just because of the cohesion of the water, but let's say, let's take 4 baseballs. Let's put them in space 1,000 miles above the Earth. And then let's say they're in a diamond pattern and they're each 100 miles apart. So you got 4 astronauts, they're up in space, they're each 100 miles apart, and each one of them is holding onto a baseball, and they let go all at the same time. Those baseballs start falling toward the Earth. Well, the one on the bottom is going to fall faster. So the diamond is going to stretch out that way. But if you drew a straight line from the center to the Earth to the baseballs that are on the edges, the left and the right baseballs, it would make a slice of pie. The baseballs aren't falling parallel to each other. They're falling toward the center of the Earth. So the closer to the Earth they get, the closer the 2 baseballs are going to get. Does that make sense?
Yeah.
Okay.
That's crazy.
If you get really close to a small black hole, the difference in gravitational attraction between let's say you're falling feet first. The difference in gravitational attraction between your feet and your head is going to be extreme. And between your left and your right, your particles, your shoulders are going to be falling on a line toward the center of the black hole. You'll get skinnier and you'll get longer. And the more tight that black hole is, the more extreme the tidal forces are. They call it spaghettification. You will literally be stretched out into a very thin, narrow strand, and then you'll be ripped apart. If you took, in fact, you can calculate this. If you take a steel rod, and the steel rod, say, is 1 meter long and has some tensile strength that it'll resist before it breaks, and you take that steel rod and you send it toward a black hole, end over end, so one end is pointing toward the black hole, one end is pointing away, you can actually calculate when the rod will snap. And sometimes it's 1,000 miles away. Sometimes it's it's usually 300 meters or a kilometer away or something like that. It'll literally be so, you're not even at the event horizon yet. You're just approaching the black hole, and the gravitational distortion is such that anything that's there will just be ripped apart. But you have to get pretty close. And you could, if you wanted to, if you shot yourself in a spaceship at a black hole, but didn't touch the event horizon, you would just slingshot right around it. You come right out the other side. In the same way we can use a slingshot of a spaceship around Jupiter. As long as you don't hit Jupiter, you could either go in front of Jupiter's orbit and its tug will slow you down, or you can go behind Jupiter's orbit, Jupiter in its orbit, and its tug will speed you up. You can do all sorts of fun things like that in the solar. You can do it to the sun. The Parker Space Probe, it was anyway, getting really close to the sun and then come really far away from the sun again and cooling off. And the next lap it would get really close to the sun and get really far away again and cool off. You could do that with a black hole. It's just a gravitational source. It's no different than any other gravitational source in the solar system, except in the universe. Except when you get too close, you start getting to relativistic time dilation problems, and your clocks get all messed up and things like that, and time slows down and whatever. But theoretically, you could zing right past one, and you wouldn't notice a difference. In fact, you wouldn't notice a difference. The people back home would notice a difference in you, but you wouldn't think anything twice. We're okay so far?
Yeah, I didn't know most of this stuff.
Good.
So much of this was informed by science fiction.
Yes. The old Disney movie, The Black Hole, that the robot Maximilian, and they're falling in. Yeah, anyway, silly. But you can't really fault people for misunderstanding, because this is weird. It's outside of people's normal experience, and it's based on some really hard mathematics that very few people in the world can actually do. And when these really smart mathematicians and scientists try to explain it, they don't always do a great job. Now, I don't know how good a job I just did, but I just tried to explain this in a very different way than anyone's ever explained it to me. Just starting off with gravity, and then the escape velocity formula, and the realization that if you have enough mass with a small enough radius, your escape velocity is greater than the speed of light. Boom, there's your Schwarzschild radius. There's your black hole. There's your event horizon. Now, one more thing. An event horizon and a singularity are not the same thing. The singularity, where all matter just congeals together into nothing but a ball of energy at the inside of a black hole. Yeah, okay, fine. But it's not the same thing as the event horizon. And really, 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 really big black holes, if you drifted into the event horizon, the tidal forces aren't appreciable. You would not be torn apart. You wouldn't be spaghettified. You just go into the event horizon. You'll never get back out again. But if you're like on a spaceship with a colony, and you have generation after generation of people, they just have generations of people. They go on forever inside. You could find a planet inside the event horizon of a black hole. And hey, let's land on this planet. And you could live there forever as a new colony on a planet inside a black hole. This is true because the event horizon, as long as we're not talking about a small compact black hole with really strong tidal forces, is not the same thing as a singularity where everything merges together and all becomes one. There's another common myth that most people probably have heard. I know in watching Lost in Space with my kids, which we absolutely love. There's some language that's inappropriate in it, and so it's not really a kids thing, but my kids love it. My youngest is is 11. She loves it. All the space stuff. Anyway, we're watching Lost in Space, and I guess at the end of the first season, the mother of the Robinson family takes herself up on a balloon to the upper edge of the atmosphere, and she's using some scientific thing, and they detect Hawking radiation. Oh, Hawking radiation only happens around a black hole. There's a black hole orbiting this planet, or orbiting the star, and it's going to come around the side of the star and destroy the planet. Oh no, we got to get off the planet. Well, she detected Hawking radiation. How quaint. Yeah. Okay, that's nice. Hawking radiation is just light. And
Wait, what?
It's just light.
That's all it is?
Yeah, it's just light. Black holes release a lot of bad things that aren't Hawking radiation. As matter falls into the black hole, the energy levels are such that black holes set out jets of X-rays. That's bad news, man. You don't want to get hit by an X-ray jet coming out of a black hole. Black holes release a lot of energy. As the stuff is falling into it, energy is coming out before it hits the event horizon. But once you're in the event horizon, this is really interesting. Once you're inside it, well, Einstein told us that E equals mc squared. That means that energy and matter are interconvertible. That means that energy can morph into matter spontaneously. Empty space is full of particles. They just pop into existence from the energy field. This is quantum mechanics. The world gets really weird when you start talking about quantum mechanics. But just assuming that energy and matter are interconvertible, then particles appear in otherwise empty space. They come out of the fluctuation of the quantum field. Well, there's a lot of energy inside a black hole. And if a particle spontaneously appears, because the particles, they appear in pairs, but if it appears just inside the event horizon, theoretically, one of those particles could do some quantum tunneling and pop outside the event horizon. Ha ha ha! And now we just lost energy. We just lost mass. So black holes should bleed energy over time. But the amount of time it would take a large black hole to bleed away its energy is much greater than any theoretical age to the universe. It's just any black hole of any size is going to be larger than the Big Bang universe, longer, and it's going to even it'll keep on going for trillions of years. And the other thing is that it's constantly, anytime a particle runs into it, gets sucked into the black hole because of gravity. So to shrink a black hole is really hard if it's large. But if it's small, the Hawking radiation is inversely proportional to the size of the black hole. So little black holes bleed a lot of energy. Little black holes can disappear pretty quickly, as in really quickly. When they started firing up the Large Hadron Super Collider in Switzerland, they actually had to calculate what happens if we make a black hole. Because those particles, when you start accelerating them to relativistic speeds, they gain a lot of mass. And when you slam two massive particles into one another, well, theoretically, you could create a little teeny black hole. And just like the Los Alamos, the Manhattan Project researchers had to do before they lit off the first bomb at Los Alamos, they had to kind of back of the envelope calculation. What's the probability of a runaway chain reaction where we ignite the entire atmosphere in a nuclear inferno? They literally did that. And they said, we don't think it's going to happen. And so they lit up the first atomic bomb. And sure enough, the atmosphere did not blow up. But they did not know it wasn't going to happen. They just didn't think it was going to happen. Same thing here at the LHC. We know we're smashing particles together. We know they got some big old masses at those speeds, and they run into each other. Theoretically, we could create a black hole, but it would be tiny. It would have almost no speed. Once one particle in one direction hits another particle in another direction, they slow each other down. The probability of that tiny little thing running into another atom even is small. And plus, at that size, they bleed away so much energy that they disappear almost instantaneously. So they said, we don't think we're going to create a black hole that's going to suck the entire Earth into oblivion. Push the button. And someone pushed the button, and they started sending particles around this gigantic ring. I'm so glad that they were right.
Right.
Okay.
Okay, I have another question.
Yes, go ahead.
Would they change over time? Like, are they going to collapse?
Yes. No.
And if collapse, what does collapsing even mean?
No. The size of the event horizon is strictly dependent upon the amount of mass inside the black hole. Now, the matter can collapse into a singularity, but you'll never see it because you're outside the black hole. The radius of that event horizon will not change. It doesn't matter what happens on the inside. The radius is solely dependent upon the mass. Now, because it's a gravitational body, it tends to accrete things. Things will fall into it, and the mass should increase over time unless it's out into the middle of absolute empty universe space. But for any given amount of time, it will be sucking things in. Therefore, the mass will increase, and if the mass increases, the event horizon is going to increase. But it doesn't change in any other way, besides the fact that it loses a little bit of energy from Hawking radiation. But, I mean, the amount of Hawking radiation is so, it's like billionths of a degree for a normal-sized black hole. You get down to, if you take something the size of the moon and you turn it into a black hole, the Hawking radiation is the same temperature as the general background radiation in space. So even something as small as, and we're talking about something that's, if the Earth is going to be less than a centimeter in radius, the moon's going to be less than that. So a black hole that's, as big as a pea is going to emit as much radiation as being absorbed from the background radiation of space. It's not going to, so it's got to be smaller than that. It's got to be something smaller than the moon, or it's going to actually get more energy than it loses. All right. What's the largest possible black hole? Is there a limit?
Can I guess it's, well, this the thing is that if I had to compare it to other large things, I would guess it could get pretty huge like a star. And stars can be tremendously larger than our sun.
But if you want to take a star and make it into a black hole, you have to shrink its size. You have to compress it greatly. The event horizon.
So then they would never be as big as the biggest star then.
Oh, no, they could be much, much bigger than that.
Oh! Huh.
Now, the lump of mass inside a black hole is not the same thing as the event horizon of the black hole. They think they can see black holes that are billions of solar masses in size, in mass. I don't know how big the event horizon on that baby is, but it's a lot bigger than our solar system. Huge. The event horizon is millions and millions and millions of miles in radius for the largest possible ones. Theoretically, you could take all 10 to the 80th particles in a known universe and compress them into a black hole. See, that's one of the things that Big Bang Theory had to get around. Big Bang Theory, before they said, oh, no, the space expands. Oh, whew, okay, woo! Because most people don't think of space expanding. They think of particles moving away from one another. That's not possible. Because if we were a singularity before the Big Bang started, we were in a universe-sized black hole. In fact, we could be inside a black hole right now. A black hole that it's so huge that it encompasses all the stars and galaxies that we see. And we wouldn't be able to tell the difference.
That is bizarre.
Yes.
So, can you have a black hole inside a black hole? And what would that mean?
I think in one of their episodes, we talked about time travel movies. And I said one of my favorite time travel movies is a movie called Primer, where they figured out that they couldn't travel in time, but if they turned the machine on, the things inside the machine would go for a long time. And if you're inside the machine and turn it off from the inside, you could go forward in time and then come back to the time when you turned on the machine. So if you turn on the machine on Monday morning, you go forward in time to Friday, and then you can go back to only to Monday morning. And in the end of the movie, they put a time machine inside a time machine. Yeah. Oh, okay. So that got weird really fast, but it made sense in the movie. So can you have a black hole inside a black hole? Wow. Because I just said the known universe could be inside a big black hole, and yet there are black holes in a known universe. Did I say something completely and totally wrong? I don't think so. But my brain is stretching to the point where I can't actually answer the question.
I think this is science happening right here on the show.
Well, as I was getting ready for this, I was dreading this exact question, where I know there's an answer, but give me an hour or two and let me go figure it out, sort of thing. And a lot of the things I've already thrown at you are things that I had to figure out over time. It took me, years to put together what I just told you, even though there's not going to be many show notes for this episode because almost everything that I've said is on Wikipedia. Literally, almost everything I said is on Wikipedia. It's not in one place. I have never seen an article that strung things together like I just tried to string them together, but all that stuff is there. It's nothing special. So, hey, if you got a question about what we just said, Wikipedia and type in the question, and I'm sure it's going to pop up. All right. So there's no theoretical limit to how large a black hole can be. Is there a theoretical limit to how small a black hole can be? Well, we've already learned that really tiny ones will evaporate almost instantly, but there is a limit to how small it can get. And this is complete math and complete theory now. And it is 22.1 micrograms. Because
wait, micrograms, would that be like
millionths of a gram?
How does that compare to? Oh, wow, that's small.
Yeah, so 22 millionths of a gram. If you would have to crush that into a size so small that you'd be smaller than the Planck length, smaller than the Compton wavelength. Matter cannot exist at scale smaller than Planck's length. So you can't have something made of matter smaller than the smallest point at which matter can possibly exist. And that number is about 22.1 millionths of a gram. I mean, Planck length is smaller than an electron, or not, it's smaller than any atom, it's smaller than any subatomic particle. It's the smallest of the small, but it's all theoretical in math. We can't measure things as small. But given this theoretical limit to size, or to mass, then 22.1 micrograms is the smallest possible black hole you can get. But its length of time, the amount of time it would last, is like, instantaneously it would evaporate. Energy would come out of it, and as soon as any energy comes out, it's gone. It doesn't exist anymore. But there might be a physical limit to how small it can get. Now, this goes, from here, we can talk about Big Bang cosmology, which might be another good episode. We could talk about some of the creationist cosmologies, like Russ Humphrey's white hole cosmology, where he's got the entire universe is actually inside a black hole. That's how it starts. When God says, let there be light, that's God stretching out the matter, and the matter starts leaving the black hole. And yet Earth, for several days, is still inside that not inside singularity, inside the event horizon. And the time dilation is such that billions of years of space-time occur in only a couple of normal Earth days. And then when the event horizon passes the Earth, boop, everything gets normal, and now all the clocks in the universe are ticking about the same rate.
So on that note then, whatever the case may be, however, God chose to maybe use black holes at the beginning or not, what would be 2 or 3 examples of why black holes exist because God made them? What would their purposes have served over time? Because it's not like black holes are mentioned in Scripture.
Nope.
But space is, the heavens are,
yes.
Stars and planets, and
yeah.
So we know he acknowledged the things we can see. So black holes are kind of mysterious. They're like the Holy Spirit of the cosmos. You don't see them, but they definitely change things.
When God made this universe, he could have made every single star exactly the same, space exactly the same distance apart, with exactly the same number of planets or not. He could have made it, like a perfect array of like a giant Rubik's cube, and every face of the cube has a star on it only, and they're all exactly spaced apart. This beautiful XYZ coordinate system. But that would be kind of boring. Why wouldn't God make a star that's just on the edge of smallness, or a star just on the edge of bigness, and he lets go, and all of a sudden it starts collapsing and it forms a black hole? Or given the physics that God invented, when he said, let there be light, he said, let there be Maxwell's equations. That's what he said. He didn't say light. He said, let there be light. Light is, by definition, behaves in a certain way. And once you have light, matter, gravity, all behaving in a certain way, well, what are all the different things you can do with it? Well, let's see. You can do this and that and this and that and that and all this stuff. In the same way, when God created life, he didn't create boring life. He said, all right, I'm going to make life based on carbon. I'm going to have this thing called DNA. It's going to absorb oxygen and burn it, and it's going to be sugar-based for its metabolism. There are these things called amino acids that make proteins. Okay, given that, what can I do? Oh, I can make birds. I can make bacteria. I can make ducks. I can make ostriches. I can make falcons. Oh yeah, and they're going to really push the envelope as far as aerodynamics. Oh, hummingbirds. Yeah. Oh, and I'm going to make some birds that fly and some that walk and some swim. And I'm going to make these things called mammals. I'm going to make some of them swim and some of them walk and some of them fly. And I'm going to make these things called reptiles. And reptiles are going to walk and swim and fly. And I'm going to make these things called fish. Yeah, fish, because they have this water thing, there's not really much land. Only a couple of fish will be able to walk, and only a couple of them will be able to fly in the air. But most of them, they're just going to be flying through water. You get my point?
Yeah.
He filled up the physics in every way possible in the living world and the non-living world. That's why black holes exist, because they're physically possible to exist. In fact, at this point, I would be surprised if we say, oh, this can exist. I would be surprised if we never find that thing somewhere within reason. I mean, you can't say, oh, yeah, a spaghettified black hole, just strings of black hole, could exist for temporarily and then it would slowly collapse into a big black hole. And, well, okay, maybe that can't because that would suck all the stars in the universe along with it. That's not what I mean. But given stars and galaxies and everything like that, God seems to have made, when he made them, he did an all possible physical. I mean, there are galaxies that don't have enough stars in them to be a galaxy, and yet they're orbiting like galaxies. There are other galaxies that have too many stars in them. They should collapse, but they haven't. They're orbiting like a galaxy. Now, is that because of dark matter? Or the lack of dark matter? Or is that just because the initial conditions that God put it up in, it's only been a couple thousand years since he made them? They haven't collapsed because it's not a billion years old. Oh, there's so many other weird and fun things to talk about with black holes, but maybe, just maybe, that's enough for one day.
Well, it's very puzzling. So I didn't expect to learn so much.
Cool.
I thought I had
that makes
the
me
basics
happy.
down. Yeah. And I kind of wonder if a black hole would be good for my throat.
No. It would not be.
Okay. I had to ask. All right. Well, thank you everybody so much for joining us on this Space Odyssey. And then if you found this episode interesting in any way, consider sharing it with your friends and family. And if you want to dig deeper into the black hole, you can find links to the stuff that Rob explained in the show notes on the website. That's available at nightowl.fm and then the podcast, so /equinox/52 for this number of this episode. The show notes are also with this episode if you subscribe to the show in an app on your phone or some other device. And you should also check out Rob's other project, Biblical Genetics. Biblical Genetics is also available on Facebook and YouTube, where you can join in the discussions with that video in the comments. And if you want to find me, I'm at JCS Darnell on Twitter, and you can tell me about your allergies, or take a listen to my other podcast, Hi-Fi, which is available at nightowl.fm/hi-fi. Until next time, goodbye, Rob.
Goodbye, Joe.
You have been listening to my irritated throat and Equinox.
You did it. You did it.
Thank you.
That was more fun than I thought. I thought it was a little too complicated in the beginning. I was getting too nerdy, too many numbers and things. But as we got into it, it started making more sense to me.
Yeah, you're not wrong. It was technical, but the further you went, the more fascinating it got.
Cool. Well, I hope we didn't lose people in the beginning.
Nah.
Get to the end. That was good.
Maybe there are people that specifically like our show because it helps them sleep. I wouldn't want to disappoint them. They just, they're like, oh, goody. There's a new equinox. I can sleep tonight. I have something special to show you.
Okay. Off air or on air?
On air. So
okay.
For the beekeeping corner of our show.
Yeah.
I am almost ready to show this to you. I think it'll blow you away. Everybody listening is going to see it in a few seconds. So hang tight.
You mean they see it and I don't? What do you mean see
They'll
it?
see it the same moment you get to see it.
How can they see it if they're listening? Wait a minute, you're getting your senses mixed up here.
No. Through the magic of editing. They'll be able to see it at the same time you do.
See it on what?
I know what I'm doing.
On their podcast?
Podcast player.
Oh. You mean the background is going to change?
The cover art is going to change for this chapter right now.
Oh, you can do that in the middle of the thing.
So this will be the
Dun, dun, dun.
chapter art for something pretty special to all of us.
That's great. I love it. That's beautiful, man. I'm gonna bring tears to my eye. Much ado about honey.
So that'll be the show art for any chapter about beekeeping.
Did you do that while we were just talking just now?
Yeah.
Wow.
So what we've been doing lately is refilling their sugar water.
Yep.
One jar every day. But we got a bigger jar because they were going through more than one a day.
Good.
Now we have a jar that lasts more than 24 hours.
Oh, I feed mine.
Mm-hmm.
I still use a little jar and I fill it up at least once a day.
Okay.
I try not to let it get all the way empty.
And so the other day, I wanted to show my son and my daughter how the bees' honeycomb was coming along. And we opened it up and we started taking out frames one at a time. And frames like 1, 2, 3 were doing really good. And too many bees to count. And a good chunk of hive or honeycomb. And, clearly still under construction, but very peaceful. They're in the orderly fashion. Okay. So you want the honeycomb to run along a single frame and not make a bridge between, say, frames 1, 2, and 3. Yeah. So what I was looking for, based on your feedback and suggestions, was any bridging. And so I checked every frame and I found a bridge between 4 and 5 and 5 and 6. Okay. So using a tool that kind of resembles a small crowbar, I just kind of reached in and split the bridging so that hopefully the bees take the hint that I don't want them to do that, kind of build it another direction.
Nah, they're going to repair it again.
I guessed they would, but all things considered, not too much bridging going on because, so let's say 1, 2, and 3 plus 7, 8, 9, and 10 had no bridges. So far, so good.
Okay. Did you see any capped comb?
No, not yet.
Okay. So you saw honey-like comb, but not covered in wax. This is not sealed up yet.
Not closed. The
last time we talked about this, you said you saw little dots, and I said, oh, those are eggs.
Yeah. Little teeny tiny yellowy pilly shaped things at the inside of those honeycombs.
Well, at this point, they should be sealed.
Oh, okay.
You also should have larvae, because they'll feed the larvae before they seal them up for them to pupate.
Oh, that's awesome.
And so you get the little dot and then some little wormy larvae things. And when they seal it up, the honeycomb looks different than the brood comb. It has a different color, different sheen, different size, different shape.
Dude.
And honey, of course, is heavier than the brood comb also. And so you'll get to the point where you can look at a thing and you can see where they're putting the brood and where they're putting the honey. And usually if they're mixing it on one frame, the honey's on the outside and the brood is in the middle. And one of the issues is that the queen doesn't like to walk across honeycomb. So she can trap herself, or the workers can trap the queen by making honey. And all of a sudden the queen's like, hey, I'm not leaving this spot. And she'll just stay in one place. And she really needs a couple of frames to be laying in, not one area, one frame. So another thing to look out for, it's really hard, is you can tell, I can't yet, I'm not this good, but by picking up a frame, you can look at the bee's behavior and say, oh, the queen's there. And then you can look at where the queen is. Even if you don't see the queen, you can tell where she is in general. You can look around it to make sure that she's got tons of brood comb around her, empty cells around her. She's not honey bound. Just little things. I got a lot to learn still too. My mass measurement, though, is not working well. The sensors don't like temperature changes, and now we just had a 32-degree day, arg. So we're still having some pretty extreme temperature swings. It's not summertime yet. I'm getting a lot of ratcheting. It'll be like, an hour or two, it's reading 22 kilograms, and then all of a sudden it pops up to 32 kilograms, and it falls down to 27 kilograms. then it's down to 21, it's up to 29, but it'll be like 3 or 4 hours of a very similar measurement, and then it pops up to another level or pops down to another level. That's just weird. Huh. I don't get it. So something is expanding and contracting and slipping or something like that, and I'm not sure that outside load cells are a good idea. And I want to try something different. I'm pretty sure that I could use a solenoid to lift basically have the scales not touching the beehive and then lift them up and push on the bottom of the beehive until the beehive comes up in the air a little bit.
Yeah.
So I can have a 0 and then lift up the beehive and weigh it and then bring it down again. So I can zero it out every single time. Or I could have a hydraulic or an air piston with just a pressure gauge.
Oh, okay. Wow.
I don't have to lift the thing up. I just got to set it on top of 4 pistons, and the pistons are just connected hydraulically to the pressure gauge. And the more mass, the more pressure's on those pistons, and they won't slide because they're sealed, but the pressure will go up. But I don't know I don't know how accurate a system like that is. I don't know if I can measure the change of a nickel's worth of pressure, or if you have to increase it by a pound or more before it makes a difference. I don't know. And I'm really tempted to just put this beehive on a giant balance or a spring scale.
Ooh, wow.
Just have it so that there's something like mechanical doing the measuring instead of all this electronic stuff that is a little sketchy when it works great inside, but you put it outside in the weather, and most of the systems that I'm trying to measure mass with are affected by temperature. And this is very frustrating. There's got to be a way to do this.
I'm not approaching it quite so scientifically, but one thing I wanted to do while the bee, we don't want to mess too much with the bee box and disturb the bees on the inside. I really am tempted to go out there and just like crack it open every 2 or 3 days and see what they're doing.
No, you don't want to do that.
I know.
No.
While we're biding our time before the day comes, we go back in there. For my son and I, we got a good book called Beekeeping for Beginners: How to Raise Your First Bee Colonies by Amber Bradshaw. And we got the paperback edition, and it has been a really good read. It is well illustrated, got great pictures, got a good writing.
Cool.
And she actually wanted to live off of her own land. So she started gardening and raising goats and got into bees because she knew how important it was for her gardening. I'm really enjoying it. I would recommend it. I'll give my final review when we're done reading it.
All right, cool. You might learn more things than I know, actually.
Haven't gotten deep into the learning part, more just the big picture stuff and the brush of the introductory matter, where she's coming from.
Yeah,
but there are some good books for the people that want to go pro. And this is not such a book. This book is more along the lines of, you have one colony, what are you going to do with it?
Yes.
And you're going to enjoy it. So here we go. Let's tell you all the ways you can enjoy your one colony.
Yeah, that's the things I don't know how to do. Split colonies, raise queens, all those sorts of technical things. And honestly, I'm not really that interested in that.
I'm not either.
I don't want to go pro. I don't want to be an expert on this little, nuance of a bee thing. I just want happy bees, and if they're happy at the end of the year, they'll give me some honey, and that would make me happy too.
Yeah.
And if they survive for a couple of years and don't give me any honey, okay, I kept them alive. You're welcome, bees.
You want to see the other one too? I also have one just for this episode.
Oh, I'll see it when the episode starts up, but you can do that.
Well, everybody else has already seen it.
Okay. Oh, that's true.
Here, check this out. And so you get to react to it now.
Okay.
So this is just the chapter art for this topic.
Oh, dude, that's cool.
Yeah, it's very cool, isn't it?
Oh.
So Rob just saw the
cover art.
The black hole cover art, yeah.
Oh, I like that. Hey, we might have to take that, rotate it a little bit, and use that as our main cover art, because I like it.
That's not a bad idea. So maybe that'll be the next version for when I update it in February next year.
All right, take that.